Control systems course is very generic in nature. This particular course, every branch of engineering student is required to go through this particular course because the concepts students learn through this particular course, they are very useful in every type of industry. That is the reason why control systems course is in different branches of engineering for the effective application of the concepts in various types of industries. Every system in nature is basically a control system because a system cannot function without control aspect of that particular system. For example, when you are operating washing machine, when you are operating a micro oven, when you are operating an air conditioner, when you are operating a television, every system is a control system because a system is one which is expected to do a specific task as designed for that particular system basing on the given input, and the system is expected to produce specific output basing on the design of that particular system. Every aspect, every task we do in our day-to-day life that can be considered as a system. For example, you are coming from your house to the university by taking a bus. From your house, when you go to the bus, that particular process, your mind knows that you need to reach the bus stop where you can catch the bus. So continuously your mind is giving signal to you where to go and what you need to do. In the same manner, every process requires an input. Basing on that particular input, the process will be executed and we get a specific output. Then what exactly each CO of this particular course is designed for? In the first CO course outcome, you are going to learn what are various types of control systems. Control systems broadly are classified into two types. One is open loop control system and the second one is closed loop control system. Once you understand clearly the difference between These two types of control systems automatically the complete roadmap how this course is designed for CO1, CO2, CO3 and CO4, you will crystal clearly understand the roadmap of this course. The advantage of knowing clearly the roadmap of this course is when we discuss each of the subtopics of various COs, you will have complete grip on the outcomes expected from each of those subtopics, and effectively the outcome you can grasp and apply to the practical situations. We discuss first what is this open loop control system by means of considering a simple example. Imagine the situation: you are riding your vehicle and you have approached 4-lane junction where there is an automatic control system located at that particular place. What an automatic control system, automatic traffic control system does, you will find in periodical time, for example, let us say 1 minute time is reserved for each of the lanes of these 4 to clear the traffic of the particular lane. Assume at a particular instant there are 100 vehicles on this lane and only 5 vehicles are for this particular lane, 20 vehicles are for this particular lane, and 1 vehicle is for this particular lane. When the traffic control system is automatic, let us say 1 minute time is given to clear the traffic here. But unfortunately, as more number of vehicles are here, only let us say some 30 vehicles could cross the junction within 1 minute time, which means there are 70 vehicles still remaining unable to cross the junction within that 1 minute time. This 1 minute time in the second lane is sufficient to clear the traffic of 5 vehicles, similarly 20 vehicles and 1 vehicle. But what is happening in this particular system is the automatic traffic control system is not bothering how many vehicles are there in each of that particular lane before clearing them. It is maintaining 1 minute irrespective of whether 100 vehicles are there, whether 5 vehicles are there, or 1 vehicle is there, 20 vehicles are there. Suppose in 1 minute time 30 vehicles only will be cleared, the problem is still 70 vehicles are waiting for their clearance, and only 1 vehicle is there in lane number 4, and unnecessarily the time is wasted when there is no vehicle on that particular lane. Hence, the control action here is nothing but that 1 minute time provided by the control system. That control action is independent of output. This particular sentence, what I am using now, is very, very crucial. The entire concept of open loop control system is reflected through this particular statement what I just made. Control action is independent of output. What is the output in this example? Output is clearance of the vehicles, the number of vehicles cleared. What is the control action? The traffic control system, which is changing its signals from one lane to the other lane in 1 minute time every time, that is the control action. It is not carrying the output. That's why this particular open loop control system is not an efficient, accurate control system always. Sometimes it may be efficient, it may be accurate, sometimes it is not accurate. For example, in this particular case, at that particular instant, depending on the traffic intensity, this system is not very accurate at this particular instant. Reason is 70 vehicles in that particular lane, still they are waiting for their particular turn. For example, the same traffic control system I am considering, but I am analyzing this control system at a different instant. At that particular instant, I found 28 vehicles here, 25 vehicles here, 30 vehicles here, 20 vehicles here. Just randomly, I projected some number at a particular instant of time. The same traffic control system it is. So what happens here? 1 minute time, all the 28 vehicles are cleared. Next 1 minute, all the 25 vehicles are cleared. Next 1 minute, all the 30 vehicles are cleared. Next 1 minute, 20 vehicles are cleared. That means no lane, no vehicle is waiting for its turn. The same control system, what we discussed in the previous example, appears to be effective in this particular case. The same control system was not very effective in the previous traffic density case. Then this particular open loop control system in this case is effective. In the previous case, it was not effective. That's why I used the statement open loop control system sometimes is effective, sometimes is not effective, but control action is independent of output. Now, I am considering a different example, and let us see what happens in this particular case of traffic control system. This particular control system is not automatic. This particular control system is controlled by, let us say, traffic constable manually. Imagine a traffic constable is located here. Let me consider the same first example where 30 vehicles are in pipeline and very few vehicles are here. Then what happens? What this traffic constable will do? By seeing the number of vehicles in pipeline in queue, this person will definitely allocate more time to clear the traffic of 30 vehicles. In the previous example of open loop control system, that system provided only 1 minute here to clear the 30 vehicles. But actually, when 100 vehicles are here, the person spends more time, allocates more time. Instead of 1 minute, this traffic constable may allot some 3 to 4 minutes to clear large number of vehicles from this 100. Then move this side and clear. Only he spends only less than a minute to clear the 5 vehicles or 10 vehicles or 1 minute or 1 vehicle. That means, what is this person doing? This person is continuously monitoring or assessing or sampling the current status of the output. The current output is monitored, sampled. In our case, out of 100 vehicles, his eyes are sensing whether 20 vehicles crossed, 30 vehicles crossed, 40 vehicles crossed, so on. That sensing by his eyes, that process itself is known as sampling the current output. And after sampling, this current status is compared with the reference output, the reference input. The meaning of compared with reference input is, the reference in his mind is, his goal is, he wants to clear, let us say, some 90 vehicles approximately. Large number of vehicles he wants to clear. Right now, he could clear only 20 or 25 vehicles. Still, good number of vehicles are to be cleared. His mind is telling him, right now you cleared some 20-25 only, still you need to clear some 60 to 70 vehicles more. That is what called comparing with the reference input. That reference input in this example is that 90 or 100 vehicles number which the traffic constable has in his mind. After comparison, what is happening? His mind is telling a signal to him saying that you need to clear still few more vehicles or 60-70 vehicles. That process of getting a compared signal, or this is technically called error signal, or this is also known as difference signal. This particular error signal or difference signal in our example is nothing but constable getting the signal from the mind. Out of 100 he cleared only 20-25, still 70-75 vehicles are to be cleared. Getting that information to his mind, that itself is known as getting the error signal or reference signal to his mind. Once that signal his mind gets, what control action he does? He allocate still more time to clear the traffic of the remaining signals. So this process is continuously happening. Every instant assessing the current status of the output, that assessing the current status of the output through his eyes, taking the corrective action by means of receiving the error signal or difference signal, and this process continues until the error signal or difference signal says you have reached your expectation, you have reached your desired output. You don't have to do this process again. You don't have to do this process now. For example, after clearing all the 100 vehicles, what does he do? He will move to the next lane where 5 vehicles are in pipeline. And obviously, he spends less time to clear the traffic of that particular lane. Like this particular system monitors the status of the output, assess the current status of the output, compares with the reference input, take appropriate control action till the desired output is attained. And this particular process of the system or this particular control system is called closed loop or feedback control system. So in this example, what we discussed just now, what is the advantage of this closed loop control system when compared with the open loop control system? Closed loop control system is ensuring the desired output. Open loop control system cannot ensure the desired output in every situation. Sometimes you may get the desired output, sometimes you may not get the desired output. In this particular example, my desired output here is I want to clear all the 100 vehicles. I have allocated sufficient time to clear the 100 vehicles. I have allocated very less time to clear the 5 vehicles or 1 vehicle, and every time I am achieving the desired output of clearing the traffic basing on the decisions the mind is taking to clear the traffic of that particular lane. So, the main advantage of this system is efficiency. The efficiency of the closed loop control system in terms of achieving the desired output is very high as compared with the efficiency of open loop control system. So before we proceed further for discussing the block diagram of open loop and closed loop control systems, let us try to identify some cases and identify whether that particular system is an open loop control system or closed loop control system. I give an example to you, and all of you need to identify whether the example I am referring is an open loop system or closed loop system. Imagine you brought one samosa to your house, and this particular samosa you want to heat it in the micro oven and you want to have a hot samosa for your eating. So one of you, what you did was you kept it in your micro oven for 2 minutes. You adjusted the timer of the micro oven for 2 minutes. And some other person, another person took the samosa and kept it in the micro oven for 1 minute. So one of you operated it for 2 minutes, the other person used the same micro oven after the completion of the first person for 1 minute. While eating, the person number 1 found it is more than the required heat and partly samosa was spoiled due to overheat. And the second person found that particular samosa had very appropriate, correct heat, and he had very tasty, comfortable heat and samosa he had. Now, The two examples I mentioned, one for 2 minutes, one for 1 minute, whether this is example number 1 or example number 2, is it an open loop control system or is it a closed loop control system is the question. So generate or have the thought process in your mind. And how can we correlate this example with the example of the traffic control systems we discussed just a couple of minutes back? This particular example of micro oven, whether it is operated for 2 minutes or whether it is operated for 1 minute, is a clear-cut case of open loop control system. Reason is the control action is independent of output. For example, in the first case, the system requires only 1 minute appropriate heat. If more than 1 minute you arrange, there is a possibility of getting overheat and the dish in that particular micro oven, it is likely to be spoiled. The taste of that particular dish is going to be spoiled. But you don't know, the person who has operated it, he is not aware that it need to be operated only for 1 minute. So randomly he kept it for 2 minutes. What is the result? The result, he got a samosa with overheat. How do you compare this example with the traffic control system we discussed? In the first open loop control system, I mentioned the automatic control system is operated for 1 minute. But how many vehicles are there in a particular lane? There are 100 vehicles. And the traffic control system could not clear all the 100 vehicles in that 1 minute time. So it is not bothered there whether 100 vehicles were cleared or not. In the same manner, the micro oven heating system is not bothering whether the required heat is attained by the dish samosa or not. As per its time setting, the 2 minutes it is operated and it has produced its result. Output is not considered by the controlling action of the system. Now, how do you correlate this example? In another open loop control system example we discussed, at a particular instant, you found all the 4 lanes 30 or near to 30 vehicles. So at that particular instant, that open loop system, though it was not caring the output, whether it has attained or not, fortunately we attained the required output in that open loop system. In the same manner, person number 2, while operating this micro oven, this particular person, what does he do? He has kept it only for 1 minute. And fortunately, that dish requires a heatness for 1 minute equivalent only. So, though it is open loop system, it has produced the desired result in the second case, and in the first case it did not produce the desired output. So this is another example of open loop control system. You can give n number of examples like this. For example, washing machine is there. You arranged the washing machine by operating the timer, let us say for half an hour, and whether you keep one cloth inside, 10 cloths inside, basing on the capacity of that washing machine, the washing machine is operated for that allocated time and produce the result, irrespective of whether 5 cloths are there or 10 cloths are there, as per the capacity of that washing machine. So open loop control systems, by this time, what you understood from these examples, controlling action or control action is independent of output. Then how do we represent the block diagram of this open loop control system? So there is a controller and there is a plant. There is an input and there is an output, and this controller and plant put together is system. What is controller and what is plant? The process or the element, series of elements, group of elements which are being controlled by the unit. The series of elements which are being controlled, they are nothing but a plant. The actual system, the actual unit which is controlling that process is called controller. For example, in the micro oven, when you arrange the timer for 1 minute, when the system starts operating and producing the required heat, that entire process of generating that particular heat is controller, and the plant, the heat is being obtained and given to that particular element in the system is nothing but a plant. For example, when you take the automotive vehicle, any vehicle you take, for example, you are driving a car, your steering is there. When you operate your steering, that is nothing but the controller. It is internally being processed, and finally the wheels of the car, they are taking the required direction, required angle of rotation, that itself indicate the plant. So when you operate the system, there will always be a controller, there will always be a plant which we put together and denote it as a system. Similarly, when we represent any closed loop control system, that closed loop control system can be represented by means of a block diagram like this. There is controller, there is a plant or process or elements, a group of elements which are being controlled by design of that particular control system in the form of the controller. This output sensing back by means of feedback elements before we elaborate briefly this particular block diagram. See, the input what we are giving to the feedback or closed loop control system is called reference input, and it is represented by usually R of t in time domain. The output what we get from the system is called controlled output, and we use the notation C of t for this. This signal, once it is sensed by feedback elements or sensor, this particular signal coming from the sensing unit is called feedback signal, and it is represented by B of t. This unit is called comparator, which compares the feedback signal with the reference signal. In the representation, when you find minus sign for the feedback signal, this representation is giving negative feedback signal. This particular feedback control system is negative feedback control system because in this system the feedback signal is getting subtracted from the reference signal. The difference signal from the comparator or summing unit. This is also known as adder circuit. This comparator or summing unit or adder, from this the signal that is coming out is called error signal. And error signal is represented by E of t. And the signal from the controller, which is controlling the plant, which is manipulating the plant. This is called manipulated control signal or controlling signal, represented by M of t. And this is the block diagram of negative feedback control system or negative closed loop control system. Whenever in the representation, in place of minus, if you find plus at the feedback input place in the summer circuit or in the comparator, that a positive sign indicate positive feedback control system. There are examples of positive feedback control systems where the input signal from the sensor will be added to the reference input and the output will be from the adder circuit will be processed according to that. One of the best examples for positive feedback control system in electronic circuits is oscillator. Electronic oscillators works on the principle of positive feedback. Of course, we elaborate this as we go ahead in the particular course. At this particular juncture, the expectation from all the students is, when you are described a particular system, when you come across a particular system, your mind shall able to assess or identify whether that particular system is a open loop control system or closed loop control system. A closed loop control system is one in which the current output is monitored, sampled, sensed, and is compared with the reference input, and basing on the difference signal, the controlling action is further initiated and the process continues till the desired output is attained. In the example of the traffic constable control system, when you correlate that example with this particular block diagram, it is very clear that the action of the significance of each block of this feedback control system. C of t, the current output in a particular lane, let us say out of 100 vehicles, at this instant only 20 vehicles are cleared. So his eyes, the feedback elements are nothing but his eyes. The eyes have sensed the current status and gave the information to his mind. This summing part, adder circuit or comparator, that itself is his mind. Reference input is what? 100 vehicles which he wants to clear. What is the feedback signal? Only 20 vehicles are cleared. What is the error signal? The mind has given the information saying that 80 more vehicles are to be cleared. What is the controller here? The controller is the traffic constable hands showing the green signal to the plant. Plant is nothing but here controlling the vehicles. The vehicles that are coming out in that particular lane, they are nothing but the plant here. He is operating the plant, nothing but the vehicles in that particular lane. Accordingly, the output is increasing, 30, 40, 50, 60 like that. Like that, every closed loop control system, there is a sensing mechanism with which the controlling action can be further extended in the time process till the desired output is attained. Then what exactly we are going to discuss in this particular CO1? Fine. When a control system is available, when we want to establish or develop a control system, or when we want to design a control system for a particular application, what is needed? That particular control system, before we go for the manufacturing process of that particular system, there is a great need for the designer to assess how the system performs really by means of analyzing the behavior of control system on paper first. We have to design the control system and evaluate the performance of that control system before we give the green signal for the manufacturing unit to go ahead with the manufacturing process. So in this explanation what I just made, I have used keywords or buzzwords. What are they? I have used model. The control system has to be modeled, and that particular model has to be evaluated or assessed. This particular process of modeling physical systems, once a physical system is modeled, for example, you all have studied basic circuit elements like resistor, inductor, capacitor, sources like voltage source, current source, etc. For example, a simple circuit you found like this. What is this electric circuit? This circuit has a few resistors and a voltage source. This is a circuit model representing some physical system. Who knows? Some series connected cells, some series connected bulbs are there to a supply. I am representing equivalence of that in the form of 3 resistors and some inductors in series with the source. Or this might be representing some other physical electrical system, who knows? Why have you studied the analysis of circuits? Why have you studied the circuit theory course? In circuit theory course, what have you learnt? How to analyze the circuit by using nodal analysis, by using Kirchhoff's laws, by using mesh analysis, etc., etc., theorems, etc., etc. What is the purpose of it? By using some tool like Kirchhoff's laws, by using a tool like nodal analysis, I am able to get what is the current through this resistor, what is the voltage across the resistor, etc., etc. And in reality, this particular information is indirectly representing that physical behavior or that particular physical system. Hence, a physical system has to be modeled. Once the system is modeled, analysis of that model by means of mathematical techniques. Mathematical modeling of physical systems is an important topic of in CO1. Once you model any physical system, how will you analyze that particular model mathematically? There are three approaches, techniques available to analyze mathematically a model which is equivalent of a physical system. One is by using a technique approach called differential equation approach or differential equation technique. We analyze the model which is equivalent to a physical system. Second is we can make use of a model called transfer function approach to analyze the model of physical system. And third one is we make use of an approach called state space representation to analyze the model of physical system. Hence, in the first CO, what you are going to learn is how to analyze a model by using a differential equation approach, how to analyze a model mathematically by using transfer function approach, and how to analyze a model by using state space representation. In this whole process, if you look into the chain or the process, a model is available which is represented in the form of electrical equivalent, or a system can be represented in the form of a mechanical equivalent by using mechanical elements, and those models we will be analyzing mathematically by using differential equation approach, transfer function approach, state space approach. Hence, at the end of CO1, your knowledge is going to be how to analyze electrical models and how to represent or how to analyze mechanical models. Remember, the moment I use the word model, it represents in reality equivalent of a physical system. electrical model here, similarly mechanical model, what elements are going to be there in the mechanical model and how to represent that model mathematically for analysis, you will be learning all those things in the CO1. And we also consider how to represent equivalent of physical systems like DC servo motor and AC servo motor, and how to develop, how to get the behavior of those physical systems by means of the transfer function approach. Out of these three approaches, differential equation and transfer function approaches, these two are there in CO1, and state space representation and its entire analysis is there in CO4. So this is the brief outcome or brief roadmap with respect to CO1, which is under the head of mathematical modeling of physical systems, control systems, open loop, closed loop, and mathematical modeling. That entire thing is in CO1.